Okay, I believe we are ready to begin. So I'm going to kick us off. Welcome, those of you in the live stream. We've got a very exciting interview today. We've got the co-founder of Lightly, a company dedicated to help you better label data. I probably just butchered that. We just worked it out, and I just butchered it. Along with their lead ML engineer. Our own CTO is going to be interviewing them. I'm just going to be introducing the live stream and doing a couple of, as usual, housekeeping items. And then I will kick it to Nikolai, and we can begin the fun interview. Assuming the slides will load. Okay, here we go. So first thing I'd like to talk about, as usual, on these webinars, we like to have you ask questions in our webinars channel over on the community Slack for Label Studio. If you're not already there, you can go to this bit.ly, or you can go to our website, any of our websites, or our GitHub, or our documentation. The link to the community is everywhere. And join that, and then submit your questions as the live stream goes on. This will be up to an hour long interview, depending on how interesting it is. And if you have questions you'd like to ask of the Lightly team, please feel free to do so during the live stream. Also, we have more upcoming webinars. So this is a new page dedicated to showcasing what we're doing, at least through the end of this year. Right now, that's what we have up. We just added a new webinar for actually October 27th. Sorry, I have it in the wrong spot here. This is for October 27th. We are going to be speaking with the creator of a data platform for AI that is using the blockchain for data lineage and transparency. So you can kind of see where the data came from, who trained the data. That's going to be a really interesting conversation. That'll be on the 27th of October. And we'll have a lot more filled in here as well. So feel free to peruse that and register for the ones you're interested in. Again, they're all free. And hopefully we'll have something there for you as well. Okay, really quickly, this is the link to Lightly AI if you want to check out what they do and have it be better stated than what I just presented. So it's just lightly.ai. And then now at this point, I'm going to kick it to you, Nikolai. That's all I really had.
Okay, thanks, Michael. Yeah, thanks, guys. It's a real pleasure that you meet us today, and I hope that we can discuss a lot, even if we don't have like the infinite amount of time. But I really appreciate that you can talk a bit about what you're doing, about all stuff that you made in your previous life, in your current life, and what are implication. So in particular, I just briefly describe what is outlined in my head, and maybe we can try through this or like doing something more. So first of all, it would be really interesting to know more about self-supervision. What is it in general? What does it mean? Why it becomes so popular nowadays? Why so many geeks from the big enterprises like Google, Facebook, like Google, like I remember this model like Sear from Google, or SimCLR from SimSear from the Facebook, and the SimCLR from Google. Even two versions for that are become very popular in open source community. And yeah, it was really interesting to know why they are so diverse. What are the secret sources of all these models? And what's distinguishing all of them, and how they could be used in like data science daily routines. I mean, if you can like share maybe some of the current state of art approaches in this field, that very welcome to do this. And also, there could be very interesting to know about whether this like SSL framework, self-supervision framework, is generic enough to be applicable to every task, or it's just mostly about training the good backbones for natural language processing or computer vision task. Yeah, so that's just my general interest about the self-supervision, about what is going on in this field, and I'm totally sure you have a very deep understanding about what's going on, and a bit later maybe we can talk a little bit about what are other implications and ramifications of self-supervision related to the supervision framework, to the fully supervised task, where we need to label huge amount of data sets, and how can we mitigate that in sort of active learning loop, active learning iterations to avoid some cold start problem there. Thanks for pre-trained models in self-supervised fashion in advance. Yeah, and finally, I hope that we'll have some time to discuss some business opportunities, like product opportunities related to self-supervision, like maybe does self-supervision as a service make sense at all? And if so, is it something we're looking for a long time? And maybe we can just quickly touch the topic about how well this could be applicable to the data privacy issues, like allowing to create some powerful models upon existed data representations provided by self-supervision framework. So that's just like my general outline, but feel free to discuss all this topic and maybe you have some presentation slides or something else.
Sure. Thank you very much for the intro, Nikolai. I think we have some slides we could actually show. They might help give some rough overview. I hope you see my screen right now. I think the most interesting one is probably the question you mentioned about self-supervised learning. How long is it out there? How has it been used also previously? And what I would highlight here is basically that if you see my screen, actually, this is a slide about what self-supervised learning actually is. And if you think about it from a computer vision point of view, we use self-supervision already for a while. Maybe you heard about Google's BERT or OpenAI's GPT models. So BERT came out 2017 and basically is using self-supervised learning in the context of natural language processing. What we do there basically is, if you take a sentence of words, we can create a proxy task to train our model with. So for example, we take a sentence of words and we remove one word, and then we train the model to predict what word we actually removed. Because we already have the full sentence in the beginning, we can create a fake task for our model to learn solve this proxy task. And the great thing is, by solving this task, the model has to learn good representations of the data. So it has to understand the context of a sentence in order to solve the task. And then we can use these representations for transfer learning. And similar approaches have also been used in computer vision. One paper here from the lab of Alexey Efros from Berkeley called Context Encoders. Basically, they used a similar approach for computer vision, where you take an image and you remove some of the images, some of the pixels, and you train the model to in-paint the original image again. So trying to figure out what kind of pixels belong to the image. And the idea there is similar, that in order to solve the task, this proxy task, you need to have a good understanding of what is actually the context of the image. So in this particular example, people are playing a sports game. So you need to understand that there are humans with legs and arms. And so these methods have been out there already for a while. We have also autoencoders, but the problem previously was that the representations were not very good. So I think in computer vision before maybe 2020, 2019, we had barely success, and this really changed. And it's actually great to see that all kind of research labs now look more into this field.
Yeah, that's great. But do you think there are some reason why it didn't succeed before? And I mean, I suppose there are some differences in between how well it works in the natural language processing task, because it's discrete space and we need to explore this discrete space. And for the visual representations, it's not so discrete, and that's why it might fail in some scenarios. Or I mean, what are the implications behind why it's not so effective in the computer vision, and how well this could be mitigated in some other architectures on the models?
You want to take this one?
I think one problem is to choose a good pretext task, and for natural language processing, predicting a part of the sentence is quite good because it is clear what is a part of the sentence, but you can't translate that well to computer vision because you don't know where the objects lie. And that's why the revolution in the computer vision came with better pretext tasks, which mainly use augmentations. Already knowledge of what we need or what is a good representation. And using this knowledge helped a lot in getting good representations.
Oh, okay, see.
This is actually great because I remember back at uni, I was also working on, so I was working on a research project where we basically did in-painting of images. And the problem there was literally that sometimes the blacked out or white out area would cover an object completely. You know, like you have a scene, maybe a sports game, and we accidentally completely removed the ball. Now the question is, should the model then put the ball in there or just the grass area or something? So I think it's very not really clear what should be the goal for the model.
Yeah, sure. Like it's like badly stated task, right? It's poorly stated task for the model to. But I mean, in general, it could be predicted somehow in the context if it is only one occlusion on the grounds, and you see that there is any balls out there, so you have to create the ball in the place of occlusion. Yeah, but still, yeah, it's.
What works really well in computer vision is what Malte mentioned with these contrastive methods. So I think here on this slide you see some very rough grouping of the different approaches. The first one is predictive, right? You take part of the input data, you remove it, and you try to predict it again. Like you have a sentence, you remove a word and train the model to predict the missing word. And in contrastive learning, we create multiple views or augmentations of the input data. So you take an image and you do some random augmentations like color changes, random cropping, and you train the model in a way that augmentations from the same input image should be close to each other, whereas augmentations from other images in the batch should be far away. So you try to teach the model to solve this sort of puzzle game of which augmentations belong to each other.
Yeah, that's, but I suppose there is just one tricky thing that's confused me a bit in this approach is that, okay, suppose that we're trying to model some objects on the images, and it's highly possible that one object occurs multiple times in the same batch, right? And if it occurs at the same time, and if we augment the image, two images with the same objects, and we try to take apart these two examples by using the contrastive learning, how can we ensure that two separate objects are not belong to the same class? That's the question.
Your papers exactly approach this problem. For example, there's one paper that's swapping assignment views, which tries to like cluster a little bit the different images, and then it says if two images are different but mostly show the same object, they belong to the same cluster and they should not be pushed so far away. Or there's also the method of replacing one image by its nearest neighbor. So very similar images are again not pushed away. So this is a topic heavily under research in the moment.
Cool. Yeah, and interesting to know how far it will go, because it's really it's a good topic to explore and to do some sort of like rocket science in there. I hope and I feel that it could be okay. But and could you tell a little bit about the clustering methods Is there any powerful enough models which currently used in the fields related to clustering, which could be used somewhere, like just plug and play, where we can download something from the open source and we used this kind of the model?
So now we will just release an update of Lightly where we will have support for this SWAP model, or swapping assignment vectors. This will actually work then out of the box. I think that's a bit the challenge we faced a year ago when we started the company, because what we try to solve is helping people to understand unlabeled data and pick what they should label in the end. And solving this problem on unlabeled data required us to work on unlabeled data or figure out how we can represent it. And we use self-supervised learning for that. And the open source framework we have has actually lots of models in a very easy way to use them. So it's very easy to play around with different models, figure out how they work, read up on the corresponding papers, and basically run the experiments. Exactly as you mentioned, the clustering method, for example.
Okay, but talking about experiments, do you think, because all these self-supervised retrainers, like well known for the field, like computer vision, where we're trying to model some images or NLP. But what about if I'm working with some like custom data where I have like multiple data types combined together, or it's a completely different domain of the data, like, I don't know, audio, time series? How well the generic approach of building self-supervision, self-supervised models could be applicable there, or it just limits to some specific data types? What are your thoughts on that?
I think, for example, for audio, there are also papers. I'm not sure whether I'm correct now, but I think WaveNet also uses some, let's predict the next tokens in the audio file. So this is also basically self-supervised learning, the predictive approach. And there were also some papers combining audio with vision. I think there was one from Facebook where they took images or videos and the audio file and basically showed that this improves the learned representation to do classification tasks on the scene. So I think there is interesting research now also going on for multimodal tasks, as you mentioned it. And the great thing is, the more data you have, the more creative you can get to create this pretext task, right? Because suddenly you can try to predict video features or image features based on an audio file, or vice versa. So I think it's just opening a new large field.
Yeah, totally. Yeah, but what I like, it's I mean, in theory, it's definitely open the vast amount of possibilities. But do you think it could be feasible for training your own self-supervision, or just like if you only have like a huge amount, billions of data and billions of computing powers that can help you to do this, and of course it's just a deal of the big companies, or it's like nowadays it's possible to build your own pre-trained backbone model to use in your own task?
Lightly offers a very easy way to create those pre-trained models. So we even offer a command line interface where you can just input your data set, and then it creates a pre-trained backbone which you can use further for your classification, object detection task, or how you would like it. So it's actually quite easy, even for small companies or researchers. You don't need to be a big company for that.
Yes, I think that's great keyword. I just have a slide here from a research project we did with EPFL together with Guarin. He actually managed to use the framework and adapt it to work with objects in videos and create a good pretext task for it. And basically, what you see in this slide is, if you would just train an object detection model in a supervised way from scratch on this BDD 100K dataset, the average position is lower than if you use his method. So you can, using self-supervised pre-training, you get a higher accuracy of the model. And we also can outperform other methods which are currently state of the art. What's even more exciting is that it even outperforms pre-training on ImageNet, which is, I think, the common way to do pre-training at the moment. And we just are in this new field since 1-2 years, right? So what's going to happen now in the next years is probably that self-supervised pre-training is becoming the new standard. So we go away from this transfer learning just from ImageNet, which has been there for 4 or 5 years, right? Everything has been done using pre-trained models on ImageNet. And I think that's also pretty exciting because we can then have models trained on the data, the actual domain where we want to solve a problem. And we can then do fine-tuning with specific labels from that particular task.
Yeah, totally. Yeah, and I mean, I think this all could be, and correct me if I'm wrong, that's all could be possible because even compare with the ImageNet, because ImageNet is still the static data set. Here we can combine any sources of information from everywhere, and we can learn so many patterns before we can build some such powerful latent space inside the models, so that it could be used everywhere. And that's the reason why the performance is higher even compared with the supervised, completely supervised way. Or there are some other causes of that.
One also very interesting fact is that usually the self-supervised pre-trained models are more robust because the kind of richness of the features they learn is very high, because it's not a very specific task they learn, right? What we do is we train a model to learn very general representations of the data, and they are very very robust in the end, which is great, right? It's what we want. We want to have systems which are better suited for out of domain tasks or new tasks, basically.
Yeah, sure. Yeah, but interesting. Does it depend heavily on how well your augmentation works? Because if you just augment it in one way, could it be that in the train itself supervised thing would ruin the model because it just poorly augmented? You use the poor augmentation scenarios in there. Does it depend on an augmentation, or it doesn't depend? It's more depend on how many examples, unlabeled examples, you can see in your data sets. What's the key? What's the key source of the performance?
Choosing good augmentations helps a lot, and with augmentations you can even bring your domain knowledge into it. For example, you can, if you know that color is irrelevant, you can just have a color changing augmentation, and then this augmentation is incorporated into your embedding. So you can have color invariant embeddings, and this can help you a lot in having good embeddings. But you also mentioned the model part. It also helps to have a better model. And the new papers are like swapping assignment vectors. They are especially powerful if you have a lot of data and a lot of images.
Okay, yeah, but these color embeddings, I mean, like we can embed we can augment something in embedding space itself, not on the images, right?
We augment on the images, but we can choose an invariance towards certain augmentations in the embedding space. So that an image and an image with a color augmentation are mapped to the same embedding. Right. Yeah, that's smart.
We can teach the model, for example, in autonomous driving, if you have cars, we could teach a model to ignore the color of cars because we know it's irrelevant to detect the car. So we can do these augmentations. And there are also interesting papers using momentum encoders. For example, this BYOL paper from DeepMind, and they show that the model is less, it's less dependent on the strong augmentations than other models. And I think that the interesting concept there is that what happens is that we have some sort of student-teacher setup. So we do a distillation of the knowledge from the model, which is also a good way to train a model in a self-supervised way.
Yeah, interesting. Yeah, that sounds like a next thing where we can put our forces. Instead of like modeling the task itself, we can model the different environments or different possibilities where we can distort our data so that it become regularized in some fashion. And yeah, but still it requires like some classifier in terms of the colors, or we need to classify whether this embedding belongs to the same color. So it just opened the new opportunities for data scientists to build new models that serve some different needs rather than modeling target tasks. Okay, that's absolutely awesome. I think I really hope that it's just the beginning of the era of self-supervision, and I think we can do much more, and in the future we will see a lot of improvements in that field. I would love to touch a bit another topic just related to the applications of the self-supervision. How good the self-supervision could help us to solve like classical fully supervised tasks. Because if you can build some, like in previous product, we can build some powerful models and we can fine tune them to some specific task. Typically, it should take much less data rather than we build from scratch, as you told there. So do you think like self-supervision could be just the next step of building the good fine-tuners, or we can do something more in self-supervision scenario, like in a fully supervised scenario with the help of self-supervised learned models?
Yeah, yes, definitely. Just maybe because you touched the topic already, I think I can even make this a bit bigger maybe, or I hope you see it somehow. So basically on this slide, you would see that we compare on ImageNet, so this is for a classification task, the accuracy of a supervised model, and these are self-supervised methods. If you just take 1% of the data set, which is labeled to do fine-tuning, and if you take 10% of the data set. And what you see here basically is with 1% labeled data on the task of classification for ImageNet, we almost get the same accuracy as if you would take 10% of the data labeled without any self-supervised pre-training, which is great. Right? We can save a lot of time there, and we can get already a very high accuracy. And on the right side, you see an example for object detection on Pascal VOC. Basically here also again showing that some of the new methods outperform ImageNet pre-training. And so basically, if you want to get a really good object detection model, state of the art at the moment is pre-training with self-supervised learning and then doing fine-tuning.
Okay, and the fine-tuning happens, is it like the whole fine-tuning, or is it just some shallow fine-tuning of some specific part of the model? I mean, how it typically works, or it's like it's no learning. Sometimes maybe it could be some cases where we don't need to learn at all. We just need to pick the right example from your pre-trained embedding space. How it works in practice?
Yes, so typically we just fine-tune the head, either the classification head or the object detection head. So we freeze the backbone after the self-supervised pre-training. The numbers you see here in these two examples are based on a frozen backbone. And it's still very important that we have some data labeled and we use that data to do the fine-tuning in the end.
And it's about like 1% of the data if we want to reach the same accuracy of.
Yes, but the tricky or the new question which now comes up is which 1% do you actually label?
Yeah,
that's what we try to solve it lightly, right?
Yeah, but if we can pick the random portion of the data, that won't work, right? So we have to be as much as representative as possible, right? So
I think that goes into the direction of active learning, which is also a very exciting field, right? How can we pick the 1% improving the model the most, or how can we do this in an iterative way?
Yeah, exactly. Yeah, I wish you can move forward to shed some lights on this as well.
Sure, I think Malte is our expert in that field. So
classical active learning methods are mostly based on uncertainty sampling, which means they find out where's the model unsure in predicting, and then choose mainly samples where the model is unsure. But this has two main disadvantages. First, the model may be unsure at very similar images, and then choosing all these similar images at once does not help a lot. And second, just because the model is sure at the sample, it doesn't mean that the model predicts it correctly. So the model is not really, the model doesn't know its own faults. And that's why it's also important to choose samples which are diverse, which are not too similar to each other, and which are diverse in the sense of a representative, which means that they cover the whole space of your data set. But to solve this problem of what is a diverse data set, you need to have some distance metric between images. And this is exactly where embeddings come in, because the Euclidean distance between embeddings is a very good distance metric or similarity metric between images. So Lightly can help you choose images which are a subset of your whole data set with images which are dissimilar to each other. And you can combine them with uncertainty-based active learning. So choose samples dissimilar to each other and where the model is unsure.
Yeah, absolutely. But I guess if you're trying just from very high level understanding of how it works, I suppose that once you try to pick some diverse examples from your data sets, you can fall into some outliers somewhere. How do you tackle with this? So do you think there are some techniques which could take density into account, so that we try to pick the best, the most representative examples, but not the outliers, because outliers are also very are far away from from some examples that they could be not so interested in terms of the modeling. So how do you think this problem could be overcome?
Outliers can be something you don't want in your data set, because they don't represent the common case. But what often happens is that outliers are really the interesting case. So think, for example, about a visual inspection where you want to find the faults, where you want to find the rare cases. And there, choosing these outliers is especially important.
Yep.
If you really want to remove outliers, then also Lightly can help, because you want to know what is an outlier of images, and then you can take the embeddings and do an outlier removal on the embeddings, or just choose samples which are really close to other samples. So if you really want to remove outliers, we can these embeddings and Lightly can also help. Cool.
I actually have a question from the community I'd like to bring up, if possible. It is from a fellow Igor. I'm going to read this as best I can. So do you think that self-supervised learning and contrastive learning will close a gap with domain adaptation, with problems in domain adaptation, specifically related to computer vision? And then there's a note here saying that with respect to training on synthetic and real data. Does that make sense to you?
Yes, we're actually just about to do a research project on that end as well, with a company focusing on synthetic data from Europe. I think that's probably the most exciting field in the future for self-supervised learning. Domain adaptation, and the second part is what some people call lifelong learning. You know, like if you have a system like a robot going into a new environment, we cannot constantly take the data, send it to somewhere, label it, and then retrain the system. If you can train a model without labeling, we can train it on the spot. So we can do some small domain adaptation on the go. And basically just the very crucial examples. It's a new object in front of me. I've never seen it before. I want to know what it is. Send these examples back where the labeling is even more crucial, right? So I think this is something which we will see in the future as well, because most ML systems, especially in computer vision, are still very close to R&D. Not so many companies have productionized it yet. And the ones which productionize it, they face constantly these problems. They have new edge cases coming up. Depending on the use cases you have, if you do, for example, autonomous checkouts, you have lots of new products, lots of new packaging all the time in the shelves. So you need to adapt and retrain the system, and this can be very, very time consuming.
Yeah.
Awesome.
That's
Thank
true.
you. And just a quick plug, if anybody else wants to submit questions, you can submit them. We'll ask them. We're using our webinars channel on the Label Studio Slack, so please submit there.
Cool. I think the other point the question touched was also synthetic data. It's also something very, very interesting. I think also the community is a bit split or divided into two sections. The one section saying you cannot use synthetic data because it's not real data, so it will never be from the same domain. And like there are lots of people which just claim this. I mean, say this, right, and believe like we should not use it. And there are other sections where you have to use it. I have friends doing a PhD in robotics, and they basically need virtual environments to train a system, because otherwise you would have a drone bumping into walls for a few thousand times before it would be able to fly, which wouldn't be feasible as well. So I think that's pretty interesting.
Yeah, totally. But I mean, maybe in these simulated environments, it's quite easy to generate a lot of synthetic data, because once you have a good simulator, so it means that you can just explore all the possibilities that the agent could face in this simulated environment. But sometimes in some more open tasks, like for example, in natural language processing, where we need to generate some text, they come from the generator itself, which could be well trained, but trained on some specific task, or could be trained for just generating the next word. So I really wonder how generator could be applicable to more specific tasks where we need to generate some structured data. That would be a great topic, and that would open the new potential possibilities to explore and to augment the data itself. Yeah, it's cool. But what do you think about? I mean, it's quite clear for me how well it might work in case where we need to find some outliers or some representative examples from our data set to label, to be labeled next. But how will it work in case of like structured prediction? For example, if we're talking about object detection on images, sometimes I know that like some of the objects on my image are well recognized, but some of the objects are not well recognized, but they are lying on the same image. So how that self-supervised embedding space exploration approach could be applicable to the data which comes from the same example from my data sets, if it makes sense.
Okay. Yes, self-supervised learning for object detection tasks is also a research area currently researched a lot. So it's still a new open area. It started with self-supervised learning for classification. In general, the same methods are applicable, but work a little bit worse. But what you can also do is apply self-supervised learning only on the crops. So have only an only co-opt the objects out of each image, and then try to distinguish the different objects, and then you quickly find new objects. So then the problem is circumvented.
Oh, okay. But it means that we need to explore all the possible bounding box locations on the images, or how? I'm just wondering, can we bump into some like exponential growth problem here, or it's a bit different in this way? So because for like, say if I have like thousands of images in my data sets, I pretty know that for finding like similar examples to do contrast, or like negative examples to do my contrastive learnings, I need to scan through all these thousands of images. But if I have like thousands of images and like dozen of objects on each image, and much more hypothetical objects in my image, I can't even like this is like exponential problem where that I need to explore in my data sets. How gonna tackle this? That's what's questionable for me. Maybe you have some thoughts on that.
What you can do is, if you have, usually you can train a self-supervised model already on objects and use that pre-trained self-supervised model, and then apply it on the bounding boxes. So just put it on top, and this way generate embeddings. And then you could have a process where you go through an image and go through the possible bounding boxes, compute its embedding on top of it with a pre-trained model, and then step by step only take the objects or bounding boxes which are new, and in this way find new examples.
So I think you would lower the threshold for the object detector, right? So you would have lots of false positives and use this approach to find potential new objects.
Yeah, I see. Yeah, okay. But anyway, it's about finding some entities from the image and then compare these entities, right? So and the same goes with text, where you find some entities in text, maybe. Okay, cool. Yeah, that's really, it sounds like a more generic approach for just any sort of machine learning problems. If there will be some techniques to use it, I think we will see much more interesting pre-trained frameworks and pre-trained engines which could power the end tasks for the user, and maybe we will come up with more tasks in the fields which could be solvable by much more reasonable time. I mean, just like, I don't need billions of examples. I just need like thousands of examples to label within by myself, and I can solve this problem. That would be really great to see, and how people could leverage all this technology in the future. And speaking about the Lightly, do you think that is it some sort of the framework which could be integrated with the frameworks like Label Studio to use the Label Studio for labeling the data you find in your data set? Or what are your ideas around integration with some labeling annotation framework?
I think one of the areas which will be super crucial is this tight feedback loop, especially also in terms of active learning, where you want to label a little bit. You want to train then a system in the background. You want to make predictions and only work on refining the labels of the predictions where the model really has issues. So instead of labeling 10,000 images at once, you would label them in batches of 100 or 1,000 image, and do a few batches or a few iterations. So we have a tutorial, like Malte wrote a tutorial for that, like how can you use the two solutions together. And I think the next kind of interesting areas are, how can you look for similar images in a data set? You know, like when you draw a bounding box around an object, maybe we can look for similar objects, using these self-supervised methods to create embeddings, maybe with some proposals of where could be objects using bounding boxes, and helping you speed up this whole process. Maybe you have also some ideas, Malte.
Yeah, yes, I agree that this idea of if you have a text and clear text, you can usually hit Control F and search for parts of the text. And it would be great to have something similar for images. And with embeddings, you can do that, where you just put in an image and then hit Control F and search for in your data set for parts of the image or images which show the same. And I think this could be a super valuable technique or method which you can use for many applications.
Yeah, that's true. That's true. Totally. Interesting. Yeah, I would imagine that could be a great, a really fast way to label all the data, which more like not like one by one example, but more like, okay, I just want to find all similar examples and label them at once, like doing some sort of a cluster annotation in this field. Yeah, that's cool. That's cool. But apart from the labeling, do you think there are some other like business opportunities that will be opened by self-supervision? Do you think that could be, as I said before, like self-supervision as a service applicable somewhere, or what do you think about other applications of self-supervision and similar?
Self-supervision could also be applied in video surveillance cameras. So where usually one person has to look at 20 screens at a time and see if something interesting happens. And the self-supervision could find out, oh, these are all regular images, and suddenly you have an image which is far away from the past images in the embedding space, and then you know something interesting happened there.
So it's again, it's like sort of the search engine for the embedding for some objects. If you try to find object by your presentation, yeah, that's cool. But I mean, it's I believe that could be adapted somehow to your specific task, because even if you pre-train something and you're trying to search over the frames in some video, like your video stream completely different from what we have seen before, or what we can grab from the, I don't know, from the YouTube or somewhere else. So how do you think it might be adapted online, or could it be at all? And what are the adaptation capabilities of the cells of the frameworks, like Lightly and supervision in general?
That's actually a very, very interesting area where there hasn't been too much research openly discussed yet. Kind of this problem of continuously improving the system or online updating it. It's something very interesting, especially with video data, because what we have is we have past frames, and we can use multiple frames, for example, for tracking objects. So this is actually what we did in this research project with EPFL. So we use tracking between frames to keep crops of similar objects, and then we can use them as augmentations. And this can be very powerful to learn representations in a video stream. So you have this new dimension of time, which you can use to train the system. And then you don't need too much data anymore. So you could online just update the system and see how well the learned representations actually evolve.
Yeah, you mean to revert back the presentations to the initial data, or what do you mean from?
So basically, having a system which just continuously updates itself. I think concepts like that haven't been really explored since we have deep learning, right? Because deep learning systems are very, very data hungry, and you always have this dependency on the human to do certain interactions with it. I think now we could have the possibility to create closed systems. Not
could
sure
adapt themselves. Yeah, which could adapt themselves without intervention. Yeah, cool. But I mean, those systems should be something like edge-based adaptation. I mean, they adapt on a device itself, or they should be adapted somewhere on the servers than doing this back and forth to deliver their adapted models to the edge devices. How that will work in the future?
Yes,
How
I think there will be lots of potential for adaptability at the edge, as you mentioned it, right? So we have smart cameras which recalibrate themselves at a specific home. I think now whatever smart device you buy with a camera or a microphone, it uses the same model across all devices which are shipped. But in future, maybe we can have systems more adaptive to your voice, to your environment, your scene, the lighting conditions, and so on. And I think these concepts haven't really been possible before, because how will we solve it otherwise? It would be pretty complicated.
Yeah, absolutely. Yeah, and just maybe last question, which intrigued me it highly related to this edge or like server-based models storing and data storing, is about the privacy of the data. So do you think that since the embedding space is just like the space of the vectors consists of the numbers and they are not related to any specific sensitive information at all, do you think that might be the branch of the new technologies which could open the possibilities to build the new models which rely on depersonalized data and like private data and deal with all these privacy issues? So do you think that self-supervision could be used for these purposes, or still it's not?
I think it could, essentially, because we could have a system trained on data where no human sees the data ever, because there's no requirement for labeling. So you could literally have this independent system. And you could also use federated learning, for example, to distribute it across different organizations. And the cool thing with self-supervised pre-training is it's task independent, or more or less task independent. If you have a concrete task where you have labeling specifications, for example, bounding boxes, some companies care about occlusions. Some companies say, no, this is not an object anymore. And you have different guidelines between companies, and now exchanging data might be difficult, right? Even doing federated learning might be difficult because you have a different task to solve. But this pretext task of self-supervised learning could be very generally applicable and used across different organizations.
Yeah, that's cool. That's absolutely cool. So, I mean, I would love to talk on this topic during the whole day, but I think we should wrap up and we have, guys, thanks a lot for all this nice discussion. I think we can continue a bit later and we can organize some more talk, and I would like to dive a bit more into the details, into some specifics on self-supervision, on like effective techniques with active learning and clustering based active learning and so on, and all the ramifications which come after. Yeah, and would love to talk it later. Thanks a lot for all your answers. And Michael,
yeah,
to talk from there.
No, this is great. Thank you, guys. I think this is going to be very interesting to a lot of people. We will post the replay of this in the next day or two. Share that with you guys so you can share it in your networks as well. But thank you guys so much for your time. And Nikolai, thank you for a great interview. Did you want to end with a plug or anything specific you guys want to plug?
I think we're fine. Thanks a lot for all the support, also to our team. And what was great actually talking to you. Hopefully we can do something similar soon again.
Yeah, I enjoyed it a lot.
Awesome. Thanks, everyone.